just to talk a little bit about this title slide and the name, in fact. So this is not your grandparents' C++. I mean, we're familiar with that phrasing, bit of a meme in a way. But the car here, anybody know what the car this is? Out of interest? No? and you've seen this talk before, but it was 6 years ago. So it's the Oldsmobile Cutlass Supreme. Of course, everybody knew that, didn't they? Well, actually, the fact that most people wouldn't know that is part of the problem. Oldsmobile, originally Olds, were one of the very first car companies. They were very well known, well, particularly around the US. Right up until like the 70s and into the 80s, they were really starting to lose ground to newer brands. They were sort of doing the same old thing. They weren't really cool anymore. So they decided to put together this marketing campaign. No, there's a whole load of other stuff as well, but most people remember this ad. This one actually. This is not your father's Oldsmobile. You know, this is something for the new generation. It was a really great campaign, very clever campaign. It sort of really hit nicely. There was one big flaw, and that was the car itself wasn't particularly new. It was very much the same old thing. It was pure marketing. And of course, everyone saw straight through that. And Oldsmobile were basically out within 5 to 10 years, they're gone. So before the turn of the century, no longer in business. So most people not even heard of them now. What's this got to do with C++? We might already have some ideas in mind. C++, when I originally gave this talk, had already been through one of these, what I call Oldsmobile moments, where, yeah, maybe it's like losing ground to newer languages. There's lots of talk of, it's going to become the new Cobol. It's not evolving fast enough. You've heard all of this. I would say actually we've had, or maybe we're in the middle of the second one now. So we'll talk about both of those to go through. You know, have we had these Oldsmobile moments? How have we got through them? And what's still to come? So bear that all in mind. And there's the full advert. Okay, so this is about C++. I said we're going to talk about the history of C++. So let's go back to the prehistory, back to the dinosaurs, at least metaphorically. In fact, all through here, I'm going to use the backgrounds that are like representative of different eras in time, just as we go through. But we're going to talk about the prehistory of C++. So this was the environment that C++ was born into. And I think it's worth going back to these roots because they really tell you what the language is, even to today. These roots are still there. So a very abridged family tree of important languages. And actually, I was reading something by Bjarne Stroustrup recently, where he gives his own diagram of all the languages that have influenced C++, particularly at the start, and it's at least twice as big as this. So this is really abridged, but all of it really traces back to Algol, before that Fortran, but Algol was really where what most modern day languages that look sort of vaguely C or C++ like really get their roots from. But then it branches, and you're probably familiar with this branching elsewhere, but it goes down the CPL's BCPL line. Anybody here actually used BCPL or CPL? Ooh, a couple of people, nice. Then on to B, and C, of course. Everyone is at least familiar with C. Maybe you've actually used it, maybe you're actively using it, still in modern use today. But then the other branch, Similar. Well, we know Similar. Anybody actually used Similar, or at least played with it? No, less people have. But we know it because we know, well, this is where object orientation came from. Actually, it was floating around as ideas before that, but it was really the first language that really gave you OO facilities in what became a mainstream language. It wasn't to begin with. But actually, that wasn't there in Similar 1, which came out in 1962. It was Similar 67 that got the OO features. So that's interesting because same year that BCPL came out, and BCPL was a very C-like low-level language. Similar, a very high-level language, high-level abstractions. a certain Bjarne Stroustrup was doing his PhD thesis in the late 1970s, right here in Cambridge University, as it happens. And he was using initially Simula 67 to write a simulation of distributed machines. And he really loved the language, gave him all the expressiveness he needed. He could just write everything very clearly the way it was meant to be. It was great. Only problem was the performance sucked. So much so he couldn't actually run his simulations. So we had to rewrite it all in BCPL. And that had the performance he needed, but writing it, that sucked. He really wanted to be able to, have the best of both worlds. But it wasn't until a few years later, 1979, he got his PhD, had moved on to Bell Labs, and the opportunity came up to actually act on this impulse, to build a language, or at least an extension to a language that gave him what he wanted. High-level abstractions with low-level performance, very low overhead. And that became C with classes. So it wasn't originally C++, it was literally C, just with some extensions to give you classes. In fact, it initially called them just abstract data types. Didn't even have polymorphism, virtual functions, that sort of thing. It wasn't until actually 1983, it says 85 there, but 83, the new version of that, or a reimagining of that, became C++ and got some more features, and that became public in 1985, hence the date up there. And that's the start of the C++ that we know today. I'll actually show you a little bit of C with classes later. It's quite interesting to go back and look at that, because it could sort of take a slightly different path. But the main point of that story is this idea of low-level access to the machine, low overhead, good performance, but with those high-level abstractions. And in fact, later that idea became refined into what we now think of as zero-cost abstractions where possible. That's the gold standard of things going into C++. It's a zero-cost abstraction. But closely related to that is if you can't actually achieve a zero-cost abstraction, then you should only pay for what you use, or don't pay for what you don't use. Always opt in. And those principles really have guided the language right from the start, even if they weren't formulated in those words right at the beginning, but quite early on. I haven't always achieved them, but where we haven't, I say we, as people that are influenced in the language, where we haven't achieved them, we've kept working on it. And so actually, as the language has evolved, we've kept this in mind, and sometimes we've actually achieved them later. So these are the important principles that have guided C++ since even before it was C with classes. All right, let's actually get into the language itself a bit more. Move on to another era now, but we're going to have a look at a bit at pre-standard C++. Now, I did say we'd have a little look at C with classes. Here's an example of some code in one of Stroustrup's early papers. A couple of things to note there. Got that link.put that normally we would have double colons now. Used to be just a dot. A lot of languages have gone back to that. It's interesting, that's actually where it started. The need to redeclare base class members, so that having that link.put there at all, we don't need anymore. There's also no private or public at the time. So a few things were different, but still getting recognizable. But really, C with classes was just a preprocessor front end initially that gave you classes as abstract data types. Actually, I'll put that inheritance up there. I think that came in quite late in C with classes. It wasn't there in the very first version. And encapsulation, that also came a bit later as well. Classes was the main thing. When we did get the first version of C++, but it's still before it's standardized, then we got a lot more features in through the mid-80s and into the early 90s, particularly templates, exceptions, namespaces, multiple inheritance, all came in around the turn of the 90s. Fairly late, really, already been floating around for a decade at that point. Overloaded operators as well was not up there, but came in around the same time as function overloads. And polymorphism. So virtual functions, they came in quite early. So they're in there by 1985. And references. It was interesting. We had references quite early, but not early enough that we have the this pointer instead of a this reference. We might have finally fixed that. We'll come back to that later. Yeah, we have references. We're going to talk about them more in a minute, but we're still at this pointer. Okay, moving on. We'll come back to some of this in a bit, but the first standard version was actually around 1991 that the first standards group got together, started talking about what these standard C++ going to be like. 1988, that was finally put out in a document from ISO. But a lot of this has been brewing for a while. The language itself didn't change much through the 90s. Mostly the focus was on the library, particularly the standard template library, the STL. That was the big addition in C++ 98. We had the algorithms and the containers in third-party form for a few years before that, but most people didn't use those. So getting 1998 could just completely change the way that we wrote C++. And we'll see an example of that in a bit. If you were there at the time, if you remember all this, but if not, it's actually hard looking back to think what it was like before we had STL as part of the standard library. But I mentioned references we'll come back to. So we had them quite early on, but I think references are probably at the center of what makes C++ unique, both in good ways, but mostly bad ways. Even though they are actually they're a good feature in their own right. So I think most of you put your hands up, say you are C++ developers, and those that didn't, they've done it before mostly. So I won't spend too long on this. This will be very familiar. But okay, here we got an integer. You could take a pointer to that. So we inherited pointers from C, but you can also take a reference to it as well. And in many ways, they behave in very similar ways. In fact, if we plot a table of the different features that pointers references have, so they're both initializable, they're both assignable, as in once you've got a pointer or reference, something you can assign the value to something else. But only pointers are rebindable, as in you can point them to something else. They're the only ones that have a different syntax when you're using them. The only ones that are addressable. You can actually get the value of the pointer address, and the only ones that are nullable. So in a way, pointers are the more powerful abstraction, but they're also the more dangerous to use. They come with the least guarantees, and they're the least safe. So references are actually a good evolution over pointers. But we still have to have pointers because of the compatibility with C, but also you can't do everything with pointers, with references, that you can do with pointers. And that's another thing that we're gradually fixing over the years. We're now at a point where if we could take pointers out of the language, we probably could. Probably could do that now. Another example is if you introduce the const keyword in, now it really sort of shows up the syntax bloat with pointers, because you can have a mutable pointer, you can have a pointer to const, you can have a const pointer, you can have a const pointer to a const value. And that's just one level. Of course, you can have pointers to pointers as well. We're not even going to go there. And we're not even going to talk about where you place const either. I've done other talks on that, believe me. But put that up against references. Because references are not rebindable, they're effectively const already. So you only have to deal with references or const references. And that's it. Much simpler to reason about. So references are the preferred syntax, generally. We fall back to pointers when we need them. But often we use pointers just because they're convenient at the time, and then we run into to problems because we bring all these other features along with it. But whether you're using pointers or references, they're referring to a value. That's at the center of it. And in the case of pointers, it could be a const pointer. The value itself can be const as well, but values are at the center of this. And in a way, the value semantics are at the heart of what makes C++ C++. So we talked about pointers and references, but actually the value is the key thing. In fact, even pointers are values. But putting values at the center was a very deliberate choice by Stroustrup. In difference to other languages around at the time that treated those things as being different things, and many other languages since as well. C++ is still relatively unique in having values as objects being their own thing. I'll explain more what I mean about that later. But that gave rise, particularly through the 90s, to the technique of RAII, which I'm sure you all know stands for resource acquisition is initialization. And I think through the 90s in particular, this seemed like the defining feature of C++. This is what made it different and powerful, and we talked about it a lot. And it's still a powerful feature that we do talk about, but it's no longer like at the forefront the way it was through the 90s. Which I think is a shame, because in some ways we sort of lost track of that power. If you move to another language that doesn't have it, you tend to miss it, even if they've got features that do sort of more or less do some of the same things. Again, I won't spend too long on this, but we know how this works. It's usually the destructor we're talking about when we talk about RAII, but actually it's the initialization as well. In fact, everything that relates to value semantics in terms of the overloaded operators. But particularly the destructor, we know exactly when that destructor is going to be called. Because if this is on the stack, it's going to be at the end of the scope. Very predictable, deterministic, and that has a lot of value. So I won't dwell on that too much, but yeah, we can predict exactly what's going to be printed out in this case. We can use that with side effects for things that aren't really anything to do with value semantics. It's more about predicting when things are going to happen. But they're also an integral part of implementing value semantics, even in our own types. But it wasn't until we got the STL in C++ that we had things like stood vector that we take for granted now. Through the 90s, many of us were still like building our own containers and using raw arrays and things like the C way of doing things. And maybe we had some third-party libraries that did it. But again, the STL was a revelation, because now this is a simple value type. We don't have to worry about memory management. We don't have to worry about any of the the copying and assignment. It's all handled in a way that feels natural because of this focus on value semantics. So, stood vector, C++ 98. We want to put something into a vector. Well, in 98, pretty much the only way we could do that is with pushback. Got a few more ways since then, but back then, pushback was the only game in town. If you wanted to put lots of values in, there's lots of pushbacks. Simple, but it gets a bit tedious after a while. I mean, there were some third-party libraries that gave you a sort of a hacky way to simplify this, but really this is all you could do. In some ways, this tediousness is the cost of getting some high-level abstractions, but also getting that low-level access. So, we live with this. This is still better than writing it all by hand. Much better. So we didn't complain too much. But in some ways, it sort of hides some things as well. Looking at this, you can say, I'm putting lots of values in this vector. But the hidden part is, well, there's going to be 2 or 3 allocations going on here. If you know that, then you know, wow, I know how many items I'm going to put on. I can reserve that memory ahead of time. So you've got back that low-level access. When you know what you're doing, then you can remove this overhead that just going to the high level of abstraction gives you. So yeah, you can reserve. Okay, so we loaded up our vector with ints. Let's get another vector now, this time of strings. So string also came in as stood string in C++98. It'd been part of the standard library before that, at least since the early 90s. But it's another type that, say, manages its own heap, gives you value semantics, but it's actually more of a managed type. Again, we take it for granted now, but if you live through the 90s with C++, you were probably dealing with like 3 or 4 different string types in any given project. It was a mess. So being able to standardize on one was also a pretty big deal. So we've got a vector of strings. So now we've got 2 containers working together. They compose. That's nice as well. What we want to do here for this example is take all of those integers from the first vector, convert them into strings and put them into the second vector. Okay. So we know how many we want, so we can reserve up front. Now we're going to loop through the first vector. How are we going to do that? Well, the C++98 way, the brand new way that all the cool kids were doing, was to use iterators. Actually, iterators are, the defining abstraction of C++98. And even to this day, yes, we have newer things now. We're going to talk about those later. But iterators are still a really powerful abstraction. But it meant you had to get the begin and end from your container. Obviously, we can do that. But in C++98, in order to use those iterators, you had to spell them out in full. And they should usually be const iterators. So you're going to have stood vector of int const iterator everywhere. We wrote that a lot, and we didn't like it. So we always looked for ways around it, but we did it anyway because we got our high-level abstractions and our low-level performance, and we were happy. It did mean that we couldn't even fit the loop variable in our for loop declarations. We had to move them out of the for loop. So we had things like this a lot. I'm sure many of you remember writing things like this. All right, let's do the string conversion. So I'm going to do it using a string stream. Still somewhat idiomatic today, not the best performance, and it's a little bit verbose, but gets the job done, and it's fairly flexible. So string stream came in, as far as I can tell, in 98. I think it debuted in 98. Before that, we had stress stream. Who remembers stress stream? Okay. In fact, we still have stress stream. Stress stream is interesting because in C++98, it was added for the first time because it's the first standard and immediately deprecated in C++98. Added as a deprecated feature. The reason why? Because while string stream generally preferred, it couldn't do everything that stress stream can do. Like if you want to manage your own buffers, that sort of thing. I won't get into the weeds on that, but that's why it's still been in the standard until today. C++20, I believe, finally fixed a few things that you needed stress stream for, so it was deprecated. Well, it was already deprecated. It was, I think it's removed in C++26. I'm sure compilers are still going to give it to you for many years to come anyway. It's an interesting little sideline there. But okay, you can use string streams to convert things to and from strings and integers. We'll do that here. And then finally, let's print it out. And this time we'll use an index-based loop because you can still do those as well, of course. And use std_cout. IO streams, been part of C++ since at least 1985, right at the day one C++ itself. We had IO streams, so more type safe than printf from C, but they are definitely showing their age. So we'll look at possible replacements for that a bit later. But it gets the job done. It's printed out our strings. Okay, you can't really tell there's strings here, but you can trust me on that. So just for fun, let's see how we'd write the same code in Python. So just 3 lines of nice readable code. Maybe an unfair comparison, but I think it's nice to know, what the difference really is. This is our high-level abstractions in C++98, getting the job done. This is typical code. This is not like something I've just made for the purpose of this slide to prove a point. This is the sort of code that we'd recognize as being Idiomatic C++ 98. Still a little way to go. All right, let's move on. Talk about classes. Again, I won't dwell too long on the specifics because this is just basic stuff. But here we've got a class with a couple of members. We've got a string and a vector of strings. We've already seen those. Some accessors down the bottom so you can get them out, and a constructor. And the constructor takes the string and the vector by cons reference. Yeah, we're all familiar with that idiom. And then stores them in its members as copies. Pretty standard stuff. But yeah, it gets a little bit verbose. But again, part of the thing we're paying for here in verbosity is this difference between assignment and initialization. Making that explicit in C++ was one of its strengths. So in the constructor, you have that initialization list where we copy the values in. It's just like a different syntax, but it's there so that you can initialize the variables, member variables, rather than later assigning them. So we got some performance benefit because of that, at the cost of some quite verbose code, unfortunately. And it doesn't stop there. So because we have that vector in there, if we want to construct one of these, then we have to pre-declare our vector somewhere else that we want to pass in as an argument. There wasn't really any easy way of doing that in line. So that then we could pass it into our constructor. Whereas a string we can pass in line. So even just instantiating these can be a little bit cumbersome. Okay, we've got our object now. We can call one of those accessors. So we use the dot syntax to get at the method. Again, we're familiar with that. Of course, we could also instantiate that same object on the heap. So previously, it was a value type on the stack, and now it's an object on the heap. We use the new keyword for that. And now we're dealing with pointers, different syntax. So we've got the star in the declaration, the arrow in the access, and of course, we have to remember to delete it. Notice down the bottom corner, I'm saying now that we're back to pre-standard C++ idioms. This is how we did do it. And of course, in C++ 98, we've got our first standard smart pointer. We had smart pointers through most of the 90s, I think. I'm not sure when I saw my first one, sometime around the mid-90s, but it wasn't until 98 that we actually got one in the standard. Auto pointer did the job. So still use the new keyword, but we passed off ownership to the auto pointer. We still get the pointer semantics, so we still use arrow to access members of the object. But we don't have to remember to delete anymore. That's done in the destructor, of course. Great, everything we want, till you come to copy. If you've ever used auto pointer, you know that copy is not a copy. Copy is what we would now call a move, or a transfer of ownership. So we would actually transfer the ownership to the new auto pointer and destroy the old one in the process, which was a really clever way of doing it, but obviously very surprising behavior if you're not expecting it. And so surprising that you couldn't even use these in certainly std vector, and I think maybe other containers, possibly deck as well. You certainly couldn't use an auto pointer in a std vector. It was explicitly disallowed, and they put special code in to stop you from doing it because it couldn't keep track of the ownership, and you would lose it as soon as it started to reallocate. So think about that for a moment. We introduced 2 new containers in a standard library and then said you can't use one with the other because it's too dangerous. That's what we were dealing with. But it was a really powerful approach to ownership that we knew we wanted to do something with. We just didn't have the way to express it yet. And obviously, you know where that's going, but we will pick that story up in a bit. Okay. So that was C++ 98. At least just a little taster, give you a flavor. That wasn't C++ done. There was still a committee working away at it. Lots of things they were talking about doing, particularly on the smart pointer front. That was a big part of the early years. And in 2003, we did get C++ 03. But it wasn't really a new standard. When it was, but it wasn't a new feature standard. We think of it as like a patch or a bug fix release. It's more than a bug fix. It introduced a couple of new things, a couple of changes. Most notably, for me at least, vectors were not guaranteed to be contiguous in memory in C++98. Many of us have forgotten that or didn't know it, but yeah, they could be non-contiguous. None of them were, because all of the implementers took the obvious approach of always having them contiguous in memory. And we relied on that. So they made it part of the standard in 03. And there was some stuff around initialization that got clarified and tightened up a bit in 03 as well. But most of it was just fixes. So not really a big release. We also got something called the technical corrigendum and TR1. So the experimental library that had shared pointers, scoped pointers, and a few other things that sort of became part of what we thought of as standard C++ through the early 2000s, but weren't strictly part of the standard. But while there was lots of talk about things going on, particularly this big feature that was really going to transform the way that we do C++ called concepts, a lot of talk about that. But time was going and nothing was really happening. And in the meantime, Moore's law was still in full swing. Machines were getting faster all the time, so the performance advantages of C++ were starting to become less important. And languages like Java and Python and C# were really taking large portions of the market that C++ had been catering to. For a while, we talked about C++ OX, because we knew it was definitely going to come in that decade. And then we said, but actually that could be hex, so we've got another 6 years yet. And then very briefly, we did actually become a little bit more honest and talk about C++ 1x. But it was only briefly, because suddenly C++ 11 was here, finally. So if you skip 03, so not really a full standard, that's 13 years between C++ 98 and C++ 11. Now remember, we said that the language itself hadn't changed much even through the 90s, since the early 90s at least. So we're getting on for 2 decades of mostly just library evolution. And even that had stagnated. So how big a difference was C++ 11? Was it enough? And was it in time? So no surprise that this is the first Oldsmobile moment. C++ going the way of Cobol. Is 11 just patching it up? Well, I think we got lucky. In particular, Moore's law had basically ended at this point. I mean, carrying on multi-core, but single core, it basically ended. Very, very small increments beyond that. So we were focusing back on higher performance languages for a while, at least in some areas. And we also needed to go more multitask, multi-process, concurrent. And up until that point, C++ didn't have a thread-aware memory model. C++ 11 did. And it even had at least some basic threading primitives and the promise of these high-level concurrency libraries coming. They're definitely going to come. But at least it had the memory model in there. But what about the other features? Compared now to these modern languages like Java and C#, and how do they really stack up? Well, let's have a look at some of the features. Again, it's all going to be familiar, but interesting to put it in that historical context. So this is the example we were looking at earlier that we said, it's a bit of a boast, but we're paying that cost for performance. So have a look at the loading up the vector. All those pushbacks and the reserve. And of course, if you know the values ahead of time, or at least have them somewhere, you can use an initializer list. C++ 11. Not free, there's a small overhead to that, which often optimizes out, but not always. But most of the time, it's exactly what you need. All of that reduced to one line. Quite nice. A little thing, but it's nice. All right. What about these iterators? Having to spell out those long iterator names was a real pain. And something that really defined, I think, C++98 code. You look at any code at random, there's likely to be an iterator declaration in there. So it's great that we got type deduction. Use the auto keyword instead. We don't care about the type, which is 99.9% of the time when it comes to iterators. And it turns out many other things as well. Not everyone subscribes to almost always auto, but a lot of people do, more so these days. But certainly for iterators, that was a big win. Great. In fact, so much so we can now put them back in the declaration of the for loop. All right. What about the string conversion? So we were using string before. Well, we got toString in C++11. And again, a nice little thing, but for this sort of code, it really cleans it up. Again, if you want real performance, you're probably going to write it yourself. But as a go-to, this is the least as good as IOStreams was. And of course, the elephant in the room, we don't even need those iterators anymore. We can go straight for the range-based for loop. That came in 11 as well. We don't even have to dereference iterators. We don't see the iterators. They are there in the background. This is using iterators, but we don't have to write them. Great, that's nice. Unless, of course, you're Sean Parent, in which case, no raw loops for you. Instead, we should use algorithms, which is actually the better abstraction anyway. So in this case, std transform is the appropriate one, but that brings the iterators back. We've got the begin, we've got the end, and even the third argument, that's an iterator. That's why we use back inserter to force it into the abstraction, but it works. The interesting bit is the bit at the end, though, that I've commented out here, because C++98 would have to put either a function pointer or a function object there. So a function object really is a class or a struct with a call operator. If you're around at the time, you'd have written lots of these. You may still write them today. Not so much reasons we'll come on to. But that's it, really. A little bit verbose, but it gets the job done. And importantly, if you write it in line like this, it gives the compiler visibility of all of the code in there, which the old C way of doing things with a function pointer couldn't do. And so there was a lot of talk about how std sort in C++98 was actually more performant than C's version because it can actually inline the code that it was calling. So again, we paid the cost of the extra verbosity for the sake of that performance, but we still got reasonably high level of abstractions. But that was C++98. And of course, in 11, we got lambdas, and we could write the same code in line. And when I say the same code, it's literally isomorphic to writing that function object. In fact, it's defined that way, that the lambda basically expands to a function object, class or a struct with a call operator. And maybe we sort of forget to define it that way these days, which I think is a shame because it's really useful to think of it that way, particularly when you're trying to reason through lifetimes. But also when you want to think about closures. If you put something in the captures list, so you capture it from your current scope, but you're effectively passing a constructor argument to that function object that's been created behind the scenes for you. And then it helps you to reason about, well, I'm doing it by value, by reference. If I want to capture everything by reference, well, that's what's happening. It's just storing them as member variables. Really all it's doing. But of course, it's much cleaner to do that in line with a lambda. Great. Really nice and actually quite big feature that really helped us to have a more modern feel. But notice that captures list. I mean, how many other languages do you know that has lambdas or closures that has an explicit captures list? Not many. It's all coming from the fact that we have pointers and references in the language, and we need to be able to specify them explicitly. Do we want a pointer here, or a reference, or a value? And we have to decide that. So again, a bit more verbosity because of that. All right, the example with auto pointer, which of course C++11 was deprecated. When it had 13 years in the sun, but it was time. And we could do that because we had a better way of doing it with RAII references, move semantics. We'll talk a little bit about, but the drop-in replacement for auto pointer, of course, is unique pointer. And by drop-in replacement, I mean you literally exactly the same, except when it comes to that copy, because now the copy doesn't work. It's deleted. And deleting constructors and operators was also new in C++11. Really nice feature. Lots of really nasty workarounds before that, but yeah, so deleted copy constructor, you can't copy an auto pointer, a unique pointer, because it's unique. You have to move it, and of course stood move doesn't move, we know that. What it does do is it presents whatever you pass to it to the type system as an R-value reference that can then invoke a move constructor, which it does on unique pointer. And so we get exactly what we wanted in auto pointer without the downsides. And that was really the motivating reason for R-value references in the first place. And of course, we do lots more with it now, maybe too much. That's another topic. But for this, really nice. And if we go to our class example, where we had that constructor where we're taking things by const reference, we can add another constructor, a move constructor ourselves if we want. We can now move things into our member variables if we want to take ownership of something else. But we can also change our original constructor to take things by value and then move those into member variables. And this can actually be more performant in some cases because we may be able to remove unnecessary copies. For example, if that stood string there was invoked with a string literal, character literal, then it's only creating one stood string and moving it instead of one and then copying it into another one. So this, in some ways, has become the new idiom, and we still see const references everywhere. We probably still write them, but see more and more code like this. It's nice. So the C++11 section is probably the biggest section here because it was probably the biggest release. It's just some of the things we just talked about, a couple of other things we didn't, just some of the highlights. Const expr actually started in C++11. It's very limited in 11. You could really just do one-liners, no variables, loops, conditionals, anything like that. We could do the ternary operator, but that's about it. But still useful, still valuable. All started in C++11. What else did I miss? Variadic templates. Again, if you lived through pre-C++11 days and needed variadic templates, you know the type of preprocessor monsters you had to deal with. That was a really nice win. Even though they're a bit of a pain to work with, still so much better than what we had before. And as well as unique pointer, of course, we've got shared pointer at that point. But there were lots more features, more than even than this. This was about as much as I could fit on the slide. And these, apart from the two smart pointers, these are all language features. So C++11 was a huge change in terms of language features. I think still the biggest ever. But there are also a lot of new libraries as well. We talked about the threading facilities already. We won't talk about regular expressions. Random numbers, maybe. But yeah, we've got the hash tables, stood chrono, type traits, even the type erased function object. We were writing our own before that. So very big release for library as well, even. But possibly the biggest change that we made in C++11 was not to the language or the library, but to the standardization process. We'd waited 13 years for C++11 and nearly failed our Oldsmobile moment as a result. To say we got lucky, it didn't work out that way. But we didn't want to make that mistake again. So we changed the model to, instead of working on something until it was done, and often that never happened, of course, deciding up front what the timeline is going to be. every X number of years. Thought we'd give free a try. Seems to have worked out quite well. And if you're ready at that point, you ship. Otherwise, you skip to the next version. The so-called train model. If you're there on the station, you get on the train. Otherwise, you have to wait for the next one. Nice and simple to understand. And it means we know there's going to be a new standard every 3 years. Which also took the pressure off a bit, because it meant that when C++ 14 came around, it didn't have to live up to C++ 11, because it didn't have 13 years to gestate. It was a pretty small release, but that was fine, because we're going to have to wait another 3 years, and there'll be another one along anyway. So it just did its thing. Actually, some quite nice features in there. Maybe we've forgotten some of them. Auto lambdas came in 14. So lambdas before that could not be templates, effectively. You think of lambdas, they are just function objects. Well, a function object, it can have a templated call operator or a templated constructor. Well, now it can. But with the auto keyword instead, slightly more modern. Auto return types as well. More const expra, actually a lot more, because you can now do variables, loops, conditionals. Felt much more like normal C++ you could put in there. Still quite a few limitations, particularly around memory allocations, exceptions, that sort of thing. But you can actually get a long way. You can start to rely less on templates for metaprogramming and actually write it more in normal C++ code, at least to some extent. All came in C++ 14. And again, quite a few library features and other features as well. Shout out to Stud Exchange, often overlooked. Very small little library feature, but I think it's really worth having in your back pocket, particularly when you're dealing with like move constructors and things like that. Really helps to simplify that. Digit separators as well. I think not enough people use digit separators. Some of these are small things, but they all came in 14. But that meant we were betting on C++ 17 being a big release. And we were expecting big things of it. Things that some of them we were expecting in C++ 11, we thought they're definitely going to come in 17. We're definitely going to get concepts, finally. And we'll get ranges, and we'll get modules, and maybe coroutines. And we have big expectations. It'll be the big release. And of course, we got none of that. And worse still, we didn't really know on the outside that until quite late. So it was only really going into that final run, we thought, actually, we're not getting any of those features. It's going to be another small release. Very disappointing. But actually, I think we were surprised by what we did get. And might be a good point to pause and see where we are with the food. Do we know, has it been ordered when it's due? It's already here, is it? Okay, then I think this is a good place to pause and go and get something to eat, and then we'll find out what actually made it into 17. Okay. Okay, thanks. Then maybe I'll continue a little bit while she's out there. So what did we get in C++ 17? Well, let's take a little tour. Start with continuing our story from earlier. We had the vector of ints, and we got it down to a one-liner with the initializer list. That was pretty big. Surely we can't do better than that. Except we know they're ints, but we're still going to say int in the template argument. Unless, of course, we have ctad, class template argument deduction. So if you can deduce the type of the template from the constructor arguments, then you don't have to spell them out. And often you can get that for free. If the compiler can see it, obviously, you might have to give it some hints. There's deduction guides you can write. Those deduction guides can be a little bit more subtle than we would have liked. So it hasn't taken off quite as much as we would have liked, but it's still there. It's still a nice little thing that removes a little bit of friction. Not a big thing, but a nice thing. what about this function? So we looked at a function earlier to convert an integer to a string. What about if you want to go the other way around, convert a string to an integer? We can also use string streams for that. Don't worry about the implementation though. Have a look at the signature. Again, we were taking strings by const reference. But we can't do the thing where we take it by value and move it because we've got nowhere to move it. Now, so const ref is still fine, but even better is to use C++11's string view, which takes a pointer to the first character and a length or pointer to the last character. Actually, often boils down to less final code than taking the const ref to the string, and also more flexible. Particularly if you pass a character literal to this, no allocation has happened at all. So string view, big win. Definitely very nice. Use that. But obviously you're not always going to be able to convert a string to an integer. So you need some sort of error handling in here. Exceptions seem a bit heavyweight for this particular problem. Could use it, but often you'll want to do these sort of things speculatively. Is this an integer? If so, what is it? So in the past, we've resorted to tricks like out parameters. So we return a Boolean to say whether there's an error, but we put the result in an argument we take by reference. And if we can still do this today, it can be appropriate. If we do that, there is at least one better thing we can do, which is to add no discard. So we are at least warned if we don't consider the result of that. So that's nice. Do use no discard. But of course, in C++17, we've got an even better way, which is with std optional. And std optional is not specific to error handling, but it can be useful for this sort of thing, where you effectively want to combine that Boolean with some other value. So optional, of course, represents either the value or the absence of the value. And in use, we can treat it a little bit like a pointer. Test it in an if statement, dereference it to get the value out. But in the error case, you don't have any more information, which for something converting a string is probably fine. But in general, you might want something to convey more information about the error as well, as you might do, say, with exceptions. Well, in C++17, we didn't get much there. You could use another C++17 feature, std variant. I don't actually recommend using std variant for error handling, but you could do it. And it does at least show you std variant. So variants, instead of being a value or no value, are one of any number of different types. In this case, an int or a std domain error. And inside the function, this actually looks okay. It's just the usage that's not so good. There's different ways to use variants. Use std visit more often, the better way. But whichever way you do it, it's very verbose and tedious again. I think this exemplifies it. And it also means we've even got to capture that result outside of the if statement so that we can then use it with Holt's alternative here. And then we use std get to get the value out if it has it. But another C++17 feature we got was the init statement. So we can at least move that statement into the if statement. And now the result is scoped to the if statement. So we haven't changed the number of characters in the code, but we've at least reduced the scope. So use init statements, work in switch statements as well, quite nice. Obviously, there's a better way still to do this that we'll come to later in later C++ versions. But just to sum up, C++17 actually turned out to be a bigger release than we thought. As well as optionals, variants, and string views, 3 really key vocabulary types. Really important to have those in the language, I think. We've got things like fold expressions to make variadic templates easier to work with. Structured bindings came in quite late. Actually quite a big, nice feature to get. And even more const-expr. I think lambdas could now become, well, actually are const-expr by default, if they can be. And if const-expr, maybe the biggest one for metaprogramming. You can now do a compile time switch in normal looking code. as of C++17. So pretty nice release. And I'd say C++17 is possibly still the most widely used version of C++. People are moving on to 20 now, but a lot of people are not able to do that yet. So I think having those vocabulary types in particular is, I'm really glad they went into 17 because so many people now have access to them. So that's 17. Before we move further, it's not here yet. Okay. Oh, I shouldn't have mentioned anything. All right, then let's move on to C++20. So when I first gave this talk back in Paul's meetup, 2019, C++20 was design complete, we thought, and was, I think we had like one more meeting before it was finalized. So we pretty much knew what was in it at that point. So I was talking about it as this is what's in C++20, and this was the slide I showed. And you might spot the odd one out on there. So contracts was in, and in between me giving this talk and actually getting standardized was taken out again. So we'll talk about contracts a bit later, but we did get a lot of big features. And again, this is getting into the present, maybe even the future for some of you, so it's probably even more familiar. But I think it's worth talking about these. Concepts. We finally got concepts. Not the concepts that was meant to have gone into C++ OX that became 11. Actually something slightly different, but still really valuable. In fact, I would say, possibly of all of these, concepts is the one that probably will change your everyday C++, or should change your everyday C++, more than anything else. You may not agree with that. We can have that conversation afterwards. But concepts are, as they've been released, they're very useful with almost no gaps. There's more we can do with them, but incredibly useful feature. We'll have a brief look at them in a bit. By contrast, ranges, very big feature, very ambitious, very nice, definitely usable. We'll look at an example of that as well. But unfortunately, bogged down by sort of gaps in the abstractions. It's a very leaky abstraction, you might say. And that can be a bit of an issue, because you really don't want surprises when you're thinking, I'm going to write it this way, and it works in this case, but it doesn't in this case. That sort of sets you back a bit. That's the biggest problem with ranges. We're gradually fixing that, but in C++20, it's a bit of a rough start. In some ways similar with coroutines. We won't talk too much about coroutines. If you want to know more about coroutines, I actually do a workshop on it. Speak to me about that later. But you're probably aware of what coroutines are. It's a big complex feature for complex problems. And I don't think it's a bad solution, but it's not a complete one. In particular, especially in C++20, basically no library support. And it really needs library support. We'll get some of it later, as we'll see. But really useful feature, let down by the library support, unfortunately. And then modules. We've been waiting for modules for a long time. It's going to solve all of our problems, literally. And we've had it since C++20. And perhaps now we're starting to get to a point you might even be able to use them. But it's still early days. So there's not many large-scale usages of modules out there yet. But it will be a big deal when it happens, because it'll be the biggest change to the way that we build C++ and organize it since the start, really. Moving away from C's sort of header-based inclusion model to something more sort of linker-based. It's its own thing, really. Again, could do a whole talk or even a workshop on that. Span, probably the other big win from C++20. Seems like a little thing, like a string view, but for arrays. But it's a really important plugging of an abstraction gap. We've had string view. Span gives you the same sort of thing, a view over existing arrays, or in the future, matrices, in a much safer way than we've had before. And of course, context explorer, we can't avoid touching context explorer. So it finally got memory allocation. You can do try-catch, maybe one or two other things. So you can finally do strings, vectors. I think most of the containers you can actually do in context explorer now, as of C++20. So almost feature complete on that. Not quite yet. Oh, and a spaceship operator. Really nice feature, which unfortunately had some backwards compatibility issues. Actually, slightly changes the meaning of some existing code, still dealing with the fallout of that. But otherwise, particularly successful in that it's one of the only features that's been added to the standard and reduced the amount of wording in the process overall, because other parts of the standard can be rewritten in terms of spaceship operator. So this is the three-way comparison that you can then define all the comparison operators in terms of, and also get automatic synthesis of existing comparison operators. So really nice feature, just a shame about that compatibility issue. Okay, so a little example to give us a flavor again. So here's a template, really simple template. Don't worry about the implementation, there's not much to it, but we just want to print out contents of the container. I'm just going to loop through and print them. No problem, it's a template, so it can take a vector, pass one in, prints it out, great. But it's a template that can take anything. So if we pass in an integer, then that's obviously not going to work, because it's not a container, and we're going to get a compiler error, and that compiler error is going to be triggered right in the middle of the implementation of the template, which may not be something you're familiar with or want to deal with, or that particularly leads you to what the problem is. So that's the problem we've been dealing with for a long time. We've had some workaround solutions with SVNA. Substitution failure is not an error, which is a bit ugly and tedious to work with, has a big compile time drag. So even just from the perspective of compiler errors, this is a problem that needs to be solved. And the solution gives you lots of other things as well, which is nice. So now you can use concepts. So the simplest possible change to the code we just had to introduce a concept is to put it as a constraint on the template argument. So in this case, we're going to use std_range's input range. So that's in the standard library, does exactly what we want. Says this T must be effectively a container, something with begin and end that you can iterate through more than once. Great, that's all we need. And if it fails, you actually get, I don't know if you can read it clearly there, you get quite a nice error message. And it depends on the compiler, but it's still quite a bit there, but everything it's telling you is significant. So it's warning you on the signature rather than in the middle. And it's saying that, this candidate template was ignored because it doesn't satisfy this constraint when T is an integer. It's exactly what you needed to know. Not always as clear as that, but we are getting better at it. And it's a good source of clearer error messages. As I said, that's not the only thing you can do with concepts. You can also overload on them. And you can use the abbreviated syntax. So the biggest change to templates since the start. Don't even need the template keyword anymore. Just use auto on its own. And you can constrain that with a concept. So in this case, we do std_range's input range auto. Means the same thing. Great. As I said, we should be using concepts pretty much everywhere. Anywhere where we know what constraints you want to put on a template argument, use a concept. The built-in ones are actually really good already, and it's actually fairly straightforward to write your own. Not super easy, but with a little bit of practice, not too bad. Just have to watch out for the, what is it again? Where you have, forgetting now, repetition of words. I've forgotten the, sorry? Requires, that's the one. Yeah. It does actually have a meaning that makes sense when you pick it apart, but it just looks a bit odd. Okay, well, that's all I'm going to say on concepts. Let's say it's another big topic. So we were on C++20 still, not quite done yet. And we come back to this example that we picked up last in C++11. So we had that std transform, and we said we're still using iterators, but we do have a better way coming. And you know what that is, of course, which is ranges. And that's great. We've reduced it down to just std views transform, pass the lambda. We're pretty much done. We can pipe that into something else, or pipe the fib vector into that. Great. That's exactly what we wanted. Remember I said ranges aren't really complete in C++20. They never quite work the way you expected. So you can't actually do anything with this. If you want to put that into a vector, you sort of want to do this. But you can't. It's not as simple as that. Instead, you've got to do something more like this. So we declare a vector up front, and then we use std ranges copy, and you pass that in. Okay, it's not terrible, but it also doesn't seem to have saved us much over the iterator version now. We've got the back inserter back as well. So is it worth it? Well, yes, I still think it is. Because now we've just changed the way that we compose these together. If we want to put something else in there, like a filter, that just goes right in line. And at that point, you start to think, yes, this is actually much cleaner. This is the promise of ranges. Having to deal with the two iterators really got in the way of functional composition. The algorithms themselves compose really nicely. The code doesn't so much. Ranges gives us that. It gives us functional composition for algorithms. It's exactly what we wanted. And the syntax is getting there. There are fixes for this particular problem coming in. I can't remember if it was 23 or 26. I think 23 has something. You can do two vector or something like that at the end. It's getting there. We're plugging these holes. We've got to start somewhere. So ranges, big feature, ambitious feature. Do try it, but just be prepared for some of these little walks. Okay. Excuse me. So that's C++20. Huge release. Only giving you a tiny flavor of it. We've still got 2 more language versions to get through. Yeah, at least. So, train is leaving the station. Last time I gave this talk, actually the second to last time, C++23 was done in terms of the standards committee, but it was still with ISO. They take usually about 9 months after we hand off the standard to them to actually publish it. This time it took 18 months. So we were coming up to almost 2025 and 23 was still not out, but it's now gone out. I think it was October, November time it became the official standard. So it is done. What made it in? Well, again, I'm going to show you the slide that I first showed back in 2019 for what was going to be C++23. So some of these were more ambitious than others. Meta classes was definitely a stretch. Modular main, I don't think anybody's even heard of since then. But I think the others were actually reasonable expectations. And of all of those, this is what we actually got. Okay, more ranges, that's good. Actually, to be fair, we also got std generator. So one of the things I had before was coroutines libraries. I said that we need coroutine libraries. Std generator is probably the most important coroutine library. Generators are a really important type of coroutine. Using std generator makes it trivial to write. At least as simple as the equivalent Python. I think of that. So that's a pretty big deal. Unfortunately, we don't have coroutine task libraries yet. They're more involved. But we're getting there. So what else do we get? So like C++17, we focus so much on the things that we didn't get, can overlook how much we actually got. It is quite a lot. So let's look at some of these highlights. So std expected. I think I actually have an example of that, so I'll hold off talking about that for a moment. As well as the magnetic stuff I mentioned up there. Const expr. Actually, I forget what we got in 23, but I think there was only 2 more things after 23 that we needed, that we just got into 26. So we were almost there with 23. Std format, sorry, more std format. So std format got into C++20. Again, it wasn't really complete. C++23 really rounded that out a lot. So std format is really the modern answer to IO streams. I mentioned IO streams, been there since 1985. It's definitely due a revisit. Std format, much more inspired by the Python way of formatting. In fact, many other languages have similar formatting features. Now it's in C++20, and 23 expands on that. But we also got std print, which is basically the same formatting facilities, but with the output as well, which means we actually have a new hello world. Hello world is now std print, or std print ln, I think it is, to give you the new line as well. A lot of these, I'm not going to cover them in detail, of course, but there was an excellent, I think it's the closing keynote for C++, CPPCon 2023, given by Timo Dumla, and it was basically what's in C++23, and he covers several of these in some depth, including std print, and at the end, he actually gives us the option, what is going to be the new hello world? Is it going to be print with /n, or is it going to be print ln? I think we voted for print ln. So that's the new hello world. But definitely watch that talk if you want to get more into C++23, because it is now the current standard. MD-span, he goes into that in much more depth. In a way, it's just the evolution of span, but for multi-dimensional arrays. It's actually so much more than that. MD-span is a real masterpiece. Anybody that's worked in finance knows how the different mappings and layouts of arrays can be the source of lots of issues, particularly performance issues, and MD-span really unpicks all of that. It's really worth looking into. And it also depended on previous work where we deprecated the comma operator in, trying to remember what it was now, overloading the square brackets operator with a comma operator. We deprecated in C++20 so that we could then use it for MD-span as an actual overload, multi-dimensional square brackets operator in C++23. So multi-standard effort to get that in. Import std. Seems like a little thing, but building on modules, you can now import the whole of the standard library with just one line. You don't have to include individual parts of the standard library anymore, if you're able to use modules, of course. But this is the great carrot to help people to get there. Once your build system supports it, and you can start to move over, that's a really big win, I think, just being able to do import std. Deducing this is perhaps, question there. I think so, yes. So I'm going to come back to that anyway. I think we have a code example that will demonstrate it. So hold that thought, we'll be clear that discussion then. Thanks. So I was talking about deducing this. I think the official name is the explicit object notation. This is the answer to what if C++ had been designed with classes and references at the same time, so we didn't have a this pointer. Well, could have a this reference? Well, now you can. There's so much more as well. The reason that the paper was called deducing this is because you can also make this a template argument. And why would you want to do that? Well, if you've ever had to write different overloads for the const, non-const, volatile, you should always write volatile, nobody ever does, and they call onto each other. There's often, I think, if you do it properly, you can often have to write like 5 different versions of a function or method that do the same thing, just because you're having to use different value categories of the this pointer. What I mean by that is, like, if you have a const method, what it's really saying is that this is implicitly const. Well, now you can make that explicit. So like in Python, where you have the self argument, you can now say this and then some name, and that gives you an explicit this operator, which you can make a template. And it has some other implications. You can do recursive lambdas with it. And you can do CRTP. Anybody familiar with the curiously recurring template pattern? Yeah, ugly. Well, now you don't have to do that anymore, because when you call a method that's templated, you can actually deduce the type of this based on what the caller has, which gives you basically everything that we needed from CRTP without the CRTP. So really great feature, actually quite a big feature, again, that potentially can change the way we write C++. Don't think it's quite boiled yet, but early days for people moving to 23, so we'll see what happens. And I think that's all I'm going to talk about on this slide. I do have some of the things that didn't make it in. I'm going to have a whole slide at the moment, but these are probably the standouts. Still no contracts. Didn't make it into 20. The way they were in, took them out, said surely they should be in 23. No, not quite yet. They really need to make sure that everybody knew exactly what we're dealing with. So that's taken a while. We'll revisit that. No coroutine task libraries we've already mentioned, and no executors. Haven't mentioned these before, but well, we did sort of mention when we got C++ 11, we said there was a promise of high-level concurrency libraries coming. And this became what we started to call executors. And they were gestating for the many standard versions. They were prioritized for C++ 23. And when we start a new standard version, there's a paper that goes out and says, these are the things we're going to concentrate on. And they just pick like the top things we really, really want to try and see in this version. The executors was on that list. It still didn't make it in. We'll come back to that in the next language version. And say some of the other things were stretches anyway, so I won't put those up there. But I did want to drill into this a little bit more. So back in the C++ 17 section, we talked about error handling, how you could use std optional. I said, in theory, you can use variant for error handling, but don't do that. It's not very ergonomic. It's not a good use of std variant. But what we really wanted to do, we can now do with std expected. So in the top half, in the function, it's very much like we were using std variant, slightly more specialized. But in the usage, it's much more like using std optional. In fact, almost identical. You can test it in the if statement, you can dereference if you have a value. But if you don't have a value, you can then say .error and get the error type out. Simple as that. Nice, straightforward, easy to use. That does everything we want, doesn't it? To a point. It's a start. To illustrate the problem, come back to optional for a moment, just because it's easier to see there. But so we're familiar with optional. If you've just got one call you're making and then you test it, that's fine. But if you start using these in a number of places, you end up wanting to compose functions together that use std optional or std expected for error handling. And then you end up with code like this. And this is just only a couple of levels deep. You get deeper, you start to end up with what we call the arrow of doom. Heavy nesting, the happy path is off in the middle there, and it's hard to follow the flow. Conceptually, it's simple, straightforward. It's just hard to read, tedious to write. And yeah, exceptions are so much nicer, but there's usually a reason we want to do it this way. So this is where the monadic operations come in. And I won't go into the weeds on what monads are, but I'll show you how we can use them. So this is the same code using the monadic extensions, which are really just three functions. There's four. There's one extra one for expected, but for optional, we've got and then and transform. Basically do the same thing, but one of them is where you already have an optional and you want it to be unwrapped and then rewrapped. And the other one is where you don't have an optional already and you want to wrap something. But otherwise they're the same. And then you've got or else, that's the missing one here, that gets called if you don't have a value. But you can compose these. And that's part of what makes them monads, the composability and the fact that they are taking things from one domain and moving them into another. So things that are not optionals, move them into the optional domain or out again. That's the monadic part. That's as much as I'll say about monads for today. In usage, though, look at the difference. We have that, and this is the equivalent code using the extensions. And look at the control flow. So parseInt, which returns an optional, the top, that supplies the first value. We pass that into the first lambda, and then we pass it into the second lambda. It's sequential. You can actually see the flow in the right order. If you're not used to this style, it still seems a bit odd to begin with, but you soon get used to it. And it's actually very simple and straightforward. Expected supports all of the same operations, but one extra one as well for when you want to transform the error value. I've actually done a whole talk on this, so watch that for more details. That's all I'll say on that for now. Talk to me afterwards if you want to know more. Because we still need to cover one more language version. I didn't have this the first time I gave this talk. I did have this slide though, couldn't resist keeping it in. C++ 26. So still seems like it's a way off, but we're 2025 now. Next month, we have the last meeting where they can approve any design changes. So after that, it's just discussing the details, but it'll basically be frozen as a design from next month. So we already have a pretty good idea of some of the major things that are going in and what may make it in. So let's have a look at those. And I'll come back in 2 years and show you what actually made it in. Hopefully most of this will still be here. So stood execution. This is, it's not executors, but it's playing the same role. So this is the new answer to high-level concurrency. More specifically, structured concurrency. So in the same way that structured programming took the old, mess of go-tos and gave you structure with their familiar conditional statements and nesting and so on, you have the same thing but for concurrency with structured concurrency. It's not unique to C++. The idea is being used in Rust, Swift, various other languages, makes it safe. Basically eliminates whole classes, most of them actually, of concurrency issues if you just conform to this framework. Now we've got that in the language. It's been voted in. That's a pretty big deal. Also a pretty big library. Very, very big, complex. And actually quite a complex topic as well. It's sort of another level above coroutines in a way. So if you struggle with coroutines, you might need to ramp up on this one a bit. In-place vector, a little bit easier to understand. Basically just a vector that internally has its own storage, no heap allocation involved. It's been asked for many years. We finally have it. Indirect and polymorphic, they just got in the last meeting. These have been hanging around for at least 6 years, 7 years as well. I think pretty much the final pieces in the standard library that we need to make it nice and easy for you to create different types of value types where objects are on the heap. So if you've ever used the pimple idiom, for example, the idea where you have the class that's basically a front for another class. You store something on the heap or in a buffer or something like that. Well, indirect basically gives you that, and polymorphic is the polymorphic version of that, so it could be one of different types. But you then treat them as simple value types. So really nice to have that in the language because it's a simple thing, but also really subtle and easy to get wrong. So I'm glad they're in. Linear algebra, another huge library, mostly based on the BLAS libraries, if you know those. Anybody that's done any linear algebra will be familiar with those. Good to have that in the language. And stood SIMD. Again, that was part of the original concurrency TS, and that's finally got in to the language as well. There was a bit of controversy along the way. Finally voted in at the last meeting. Skip over pack indexing. It's quite nice, but not that important. The two question marks. Contracts and reflection. Contracts still on track. And we're at the final hurdle. The next meeting decides whether it goes in or not. And they've done all the work. They've done hundreds of papers to discuss every little detail to death. They weighed everything up and they presented the almost inevitable conclusion of all of that work. And right now, I can't go into too much detail because I don't know how much of it I know from channels I'm not meant to talk about. But there is a movement within parts of the committee to try to shoot it down. We're going to see where that goes. What I will say is, and this all came together the last week or two, so it wasn't planned that way, but next Monday, we're having a special meetup at C++ London, so if you can make it into London, do come along, where most of the contracts study group, and a few other interested people, are going to come in for an experts roundtable to talk through all of this stuff. So if you want to be right in the middle of the controversy, come to London next Monday. See the C++ London page. So that's all I'll say on contracts for now. Reflection is having a bit of an easier time. That's definitely on course for 26 as well. Hopefully we'll get in next month. There doesn't seem to be any reason why not at this point other than us just running out of time. But I think it's been prioritized enough, that shouldn't happen. So unless we find any big flaws in it, we should get reflection in C++ 26. And that alone will make this a huge release, because this will definitely change the way we write whole classes of programs. Really need a whole evening just to talk about the implications of that. But we can talk about that afterwards. So just very, very briefly, because I've got two more characters up there worth talking about. Underscore. So the placeholder name. Now you've been able to use underscore as a variable. So how can we repurpose it? Well, they've done it in a really clever way. If you don't reference something that's named underscore, then you can use the name more than once with no warnings. And that's it. And that means you can use it anywhere you don't care about the value. Think of different like RAII types, like locks and things like that. Structure bindings, you don't care about an argument. Lots of places where you can use this, and now you can. And it's just a really simple way, and we got the thing we wanted, underscore. So that's nice. Dollar, that is now a legal identifier, or part of an identifier, and a few other characters I think we've got as well. Seems like a little thing, but opens up some possibilities. So that's quite nice. They're all in. So really it's just contracts and reflection that we're really waiting for in Hagenberg next month. So I'll update you next time on that. That's where we're going with C++ 26. So I've got, I think, a couple of minutes because we are going to need to get out quite quickly. But I did want to mention where we are in terms of an Oldsmobile moment. And I think contracts is right at the heart of this. But even bigger than just contracts is, and you've probably heard the topic of safety in C++ being talked about a lot. So again, it goes right back to at the start. We talked about pointers and references really being at the heart of what characterizes C++, but also what's most dangerous about it. That low-level access, things like uninitialized variables, all types of UB, undefined behavior, they're all there in the language for a reason, at least historical reasons, but they're also huge problems in terms of particularly vulnerabilities that can be manipulated. So there's a big push inside and outside the committee to make C++ safer by addressing individual things like uninitialized variables. We've actually got a pretty decent solution to that. It's also in 26 already, called erroneous behavior, which is a more formalized version of certain parts of undefined behavior that take away the vulnerability aspect of it. But there's also another push to make it memory safe in the same way that Rust is. Even like adding a borrow checker, that's having a bit of a rougher time. Not least because it will be at least until 32 before we even start to see that. But that's the big topic at the moment. The feeling is that if we don't get these things in, then that is pretty much it for C++. It will go the way of Cobol in the next half a decade to a decade. So we are in the middle of that moment at the moment. So we can't say which way it's going to go, or even if it will. But there are definitely forces at play that may dictate the fate of the language. So very exciting time to be in the community, or interesting time in the Chinese sense. So I'll leave you with that thought and say thanks very much for staying with me and for being part of this first event. Hope you'll all come back. Thank you.